Okay, so is this working? Okay, so okay, so I first want to thank the organizer for this conference in memory of Jean-François. As you know, Jean-François was my PhD advisor and then was a friend, and I owe him so much that I'm really happy to can talk in this conference. So what I want to talk about today is about insider trading. Why is it important to speak about that? Is that basically, if you want to detect those on the market, you need to know how they behave. So this is a reason why it's important. But it is maybe not the most important reason of this analysis. In fact, there is another reason, which is that informational asymmetries are everywhere on the market. Okay, and think of typically institutional investor that are much better informed than private investor, because institutional is services of analysts working for them. So this is services that private investors do not have. And so de facto there are asymmetries. And so we are in a situation where we have well identified informed players that are observed by the other to take to deduce from their move some information. And therefore, what I'm believing is that those information asymmetries are in fact driving the price on the market. And so the question I want to ask today is how those strategic behavior by the informed agent will influence the price dynamic. And as you will see, I will try to give a very precise answer on that. And this will affect the first analysis, a former paper by me in 2010, where I show that in a risk-neutral market, where every individual are risk-neutral, basically, the price process should be what I call a continuous martingale of maximal variation. I will explain what it is later. But it involved basically a Brownian motion. And what I want to show you today is that, in fact, this class of process is, in fact, very robust to change of models. And in particular, it will also appear when there is risk aversion in the market, the same class. Okay? So let me just go over the first idea of the paper. The idea was just to see the market as a two-player game, where player one is a risk-neutral informed investor, and player two is just the remaining part of the market. Okay, so player one and two are trading a risky asset R against some numeraire N. There is an initial information asymmetry. Player two received a message, player one received a message M that has some probability distribution. And player two is not informed about M, he just knows the law of that message. And clearly, this message will influence what I call the liquidation value of the risky asset. So at a future date D, the message will be made public. At that time, when everybody will know that message about the firm, well, at that time, the value on the market of the share R will be L, which is a function of M. Okay? And we assume that this function of M, L, is known by both players. Okay, so in fact, the only part of the message for the game, what is relevant for the game, is this value L of M, which has some probability distribution mu. And so we can replace the first stage of the game by a simpler one, where basically nature select L with probability mu. Player one is informed of L, not player two, and both players know the law. Then, after these first informations, stage, I consider n transaction between the player before before the revolution date d. And to make those transactions, they use what I call a general trading mechanism. So it's completely general way to model the trade. Both player have action spaces, I and j, respectively. And t is a transfer function. So TIG is just the transfer that will occur if both its actions are I and j. So it will be a number Aij of share of the risky asset and a number of unit of numeraire Bij that will transfer from player 2 to player 1. Okay, this is a transfer that depends on action. Okay. So at stage Q, both players choose simultaneously their action. The pair is then IQJQ is publicly announced, and the portfolios are incremented. So YQ is portfolio of player 1. YQR is the number of unit of risky asset, and YQN is the number of unit of numeraire in player 1's portfolio. So YQ just becomes YQ minus 1 plus what you get at that period. Okay, so this is a very simple model. Okay, so what is now the objective of the players? Well, for player 1, it's quite clear. It's a risk neutral, and what he wants to maximize is the expected liquidation value of its final portfolio. Okay, so this is L, the liquidation value of asset R, multiplied by the number of share of R he has in the portfolio at that time, plus the number of units of numeraire that was 1. Okay, so player 1 aims to maximize this expectation. Now the problem is that player 2 is not a single player; it's a coalition of players. What is the payoff function? Well, in fact, what is clear is that a payoff for player 1 is clearly a loss for the remaining players. So it is quite natural in this setting to consider that player 1 will play in a cautious way and will play basically his max-min strategy as a first approximation, at least. And this, in fact, amounts to look at the equilibrium of the zero-sum game, where a risk-neutral player 2 aims to maximize the liquidation value of his own final portfolio. So we are, in fact, back then to a zero-sum game. And so now what are the results we can get from that game? I have to make some assumption on the transfer function to be realistic. And I will not, I have just 5 assumptions that are quite general. The first one is simply that it's invariant with the scale of the numeraire. The other one is that the value of the gain should not depend on the riskless part of a risky asset. So I will not enter into the details here because this is not the center of this talk. Next is the fact that the game has a value and both players have optimal strategy. The next assumption is that there is one situation where player 1 can take benefit from this information. And the last one is just an assumption about the continuity of the value of those games. Well, then, well, I will just skip that. Then, well, I'm nearly ready to give my result on those. Denote Vn, the value of the game of length n. I have to define what I understand by price in this setting, because players are using abstract strategy space. What is a price? And in a risk-neutral game, it is quite natural to define the price as the expected liquidation value given what the uninformed player has observed. Okay? This is exactly the price at which you would agree to exchange with another player with the same information. Okay. So now what is a CMMV? It's simply a martingale, pi t, which can be written as function, as a function of bt and t, b being a Brownian motion. Okay. So since it is a martingale, f has to satisfy the heat equation, but this is just technical. And we further require that this function f is increasing in the Brownian variable for fixed t. Okay. This is the definition. Now, it's also interesting to note that given a final distribution mu, there is only one CMMV having such that the value at time 1 of p mu is mu distributed. Okay, so final law determines the whole past. And this is very important to application also. Now, theorem. If the exchange mechanism is natural, if you consider any sequence of equilibrium in this game, now sigma and tau n being an equilibrium in a game of length n, if you look at the price process at equilibrium, and you represent this discrete time process by continuous time process pi and t, which jumps to the next value after each interval of length 1 over n, okay, then this process, this continuous time process, converges in law to the CMMV p mu. Okay, and so this is completely independent of the asymptotic is completely independent of the trading mechanism you use. Well, the only condition is that it must be natural, but those are quite general assumptions. Okay. So this was the result of the previous paper.
The 5 bullets you had at some point?
Yes. Yes. That's natural. Okay. So, but you get always the same asymptotic distribution. And what is, well, a byproduct also of this analysis is that Vn divided by square root of n converges to something finite. So Vn itself goes to infinity, if you look at that. So you have to rescale Vn, the value of the n stage game. You have to rescale by square root of n. And this is, in fact, what we will do to introduce risk aversion. Now, in the previous game, the player 2 was aiming to minimize this quantity, basically. Okay, can divide by square root of n, there is no problem. But now, I will introduce in the new game, where basically we will introduce a utility function or the final value. And this utility, since I still take place to minimizing, to introduce risk aversion, I have to take the utility function h, C1, strictly increasing and convex. Okay. Now, what is the price process? Here in this setting, I can't use the previous trick to say it was the expected value, because
player 1 is still neutral and maximizes that.
Yes, but player 1 knows the final value. So
only player 2 now has a different payoff.
Yes, but at the end we could also introduce a utility function for player 1. There is no change there. And
the game is no longer zero sum.
It is no longer zero sum. Yes. Okay. So what is the price process? Well, I can't work in that generality. The idea here is to go to a specific trading mechanism where prices appear naturally. Okay. Yeah. Yes. The value is positive, so it's a zero-sum game. Player 2 is losing. Yes. Well, this is true that it is unnatural, but in fact, it has to see where one of those assumptions was positive value of information, which tells you that there is at least one situation where information is profitable for player one. Okay. Now, it seems to be quite obvious in practice that players are paying to get information, which seems that to have as a corollary that it has some value. You know? But so what I could say, player two is not fully rational in a sense that it is a coalition of players. There are maybe inside this coalition there are liquidity trader trading for other reasons. Yes, but we are, in fact, the idea here is that we are working in constant, at a constant time, I mean, constant dollar. Okay, so we have to turn to a particular price-based mechanism, and the idea here is just to consider player two as a risk-averse market maker. So at each period, he has to post a price PQ for 1 unit of the risky asset. Okay. And the player one is a risk-neutral informed trader. At period Q, he decides to buy, that is UQ equal 1, or to sell 1 unit of R. Okay. And the idea is just to analyze the asymptotic of the price process in this game. So, as before, stage 0, nature select L with probability mu. Player 1 is informed of L, not player 2. Both players know mu. At stage Q from 1 to N, both players select respectively UQ in -1, 1 and PQ in R. The choices are simultaneous, and after they are made, they are observed publicly before going to the next stage.
Player one decides to trade before knowing at what price.
You could, player one could choose, there is no change, in fact, you will see this later. He could decide after observing the price of player two. Okay? This would not change the conclusion, but it's easier to present the game like that and to work with it. And now what is player one's payoff? Is the sum, each time he's buying UQ is 1, okay? And then he gets something that is worth L, but he has to pay PQ for it. Okay, so this is just the game we are considering. And player 2 aims to minimize the expected age of this function, of the same amount. So this is a well-defined game. Now, the price process in a game of length n, I had a superscript n here to say that we are in a game of length n. And you can represent this by a continuous time process as before, pi and t. And now I'm ready to present you the results. The first one is that there exists a sequence of equilibrium in all games. There is an equilibrium, and we can consider a sequence of those equilibrium. Now, the second result is that denote Pn the probability distribution of the price process at equilibrium. Okay? And my next result is basically that Pn is compatible with the classical no arbitrage theory. And let me just remind you that Harrison-Pliska results just tells you that there is no arbitrage if and only if there exists a martingale equivalent measure Qn, that is a measure that has a strictly positive density with respect to Pn, such that the process of price is a martingale under this Qn. Okay, this was Harrison-Pliska result. Well, our first result, well, our second result is that our equilibrium is the same flavor in the sense that there exists a probability density which is strictly positive, such that the process pi n is a martingale under this new probability. Okay, and furthermore, this probability is unique. Okay, this in arbitrage theory also has an interpretation, but I will not enter there because arbitrage has no meaning in this model. And what is the next result is that if you look at the process under this martingale equivalent measure, then the process pi converges to a CMMV as before. Okay, so it gives you the law of the price process under the martingale equivalence measure. And this is very important to price options, and okay, under the martingale equivalent probability, the actualized price process should be a CMMV, actualized because I'm working in actualized price, essentially. Okay. So let us just give you a flavor of the proof, because although the game is quite simple, the analysis is a bit technical, and I apologize for that. So what our strategy, we have to allow for mixed strategy in this game. So a strategy is a sequence, a behavior strategy, sigma 1 to sigma n, where sigma q just map player 1 information at period q, which is L, the liquidation value, and the previous moves by both players, to a probability distribution of his next action. We have the same notion of strategy for player 2. Well, the only difference is that player 2 does not observe the L, and it chooses a probability distribution over R. When you have mu plus a pair of strategy for both players, we have a probability on the whole history that I denote pi mu sigma tau. Okay, and the payoff, the payoff of player 1 is just the expectation under that probability of its payoff function that we described before, and the same way for player 2. Okay. So to analyze this game, the first idea is to analyze a simpler game that I call the reduced game, where in fact player 1 does not observe what player 2 is doing at all. Okay, so a reduced strategy for player 1 is now a map where at period q is just decide to choose his next action as a function of L and of his past on action, but he has not observed player 2's action. Okay. And I have a lemma, which is if there exists an equilibrium in this reduced game, then there exists also an equilibrium and a pure strategy of player 2, P bar, such that sigma star P bar is not only an equilibrium of the reduced game, but it's an equilibrium in the previous game. Okay. Yes, we use. Yes, we use Jensen's inequality exactly, and the convexity of H. So I will skip the proof since you already got it. Now, this is just a result of Jensen's inequality, and so now, what is take sigma to be a reduced strategy of player 1. In fact, since he is not observing player 2, he can choose his action before starting the game. Okay, and so its amount with mu, it generates a probability distribution on L and the history of his actions, and we can what we know is that the marginal of pi, the marginal distribution of L under pi is just mu. Okay, but if you know pi, you can recompute sigma and vice versa. So we can identify a strategy of player 1 sigma with the corresponding pi. Okay. Now, finding a best reply to a given strategy of player 2 is basically solving an optimization problem in pi, the variable is pi, but with a marginal constraint on the marginal, okay? And as you know, when there are constraints, you consider the Lagrange multiplier, okay? To look at an unconstrained problem with Lagrange multiplier. And this lead, in fact, this is the idea that appears under the dual game. And so we know we'll have to consider a dual game. And what is a dual game? Let psi be a continuous function. Player 1 now select pi without any marginal constraint, and player 2 select a pure strategy p bar. And the payoff of player 1 in this dual game indexed by psi, resulting from the pair of strategy pi and p bar, is just the payoff in the primal game minus psi of L. Psi of L is in fact the Lagrange multiplier associated with the control at L, basically. This is the idea. Okay, so it's a penalty for player 1 for having chosen that state. Player 1 basically is choosing L, but he has a penalty psi L if he chooses that particular L. Okay, this is the idea. And so why is it important to analyze those dual games? Well, first of all, if we have an equilibrium in this dual game that by change for some psi has the right marginal, then it is also an equilibrium in the primal game. So the idea is to analyze the equilibrium in the dual game, which will be much easier, and then to show that for some mu, for some psi, you will get this for the equilibrium. Okay, so if pi is the best reply to a given strategy, basically player 1 is choosing the whole history of U and L. Okay, now suppose that U has been fixed and you want to get the optimal L, then basically from this formula you see that player 1 will choose L solving this maximization problem, psi star of x, where x is in fact the coefficient of L, which is the sum of UQ divided by square root of n. Okay, so the optimal L must solve, given a fixed history, must solve this optimization problem, which is, by the way, Fenchel transform of the function psi. Okay, and since the payoff, since psi basically will only appear through its Fenchel transform, it shows you that we only need to consider convex psi, because they have the same, the convexification of a function has the same transform, the same Fenchel transform. So now this, the fact that L must solve this can be expressed simply by saying that L must belong to the supergradient of the Fenchel transform at that point. This is Fenchel lemma. And so if pi is a best reply, we must have this with probability 1 under pi. Okay. So now, so it remains to choose optimally the sequence of UQ. Okay, but the payoff, given a history of UQ, is now just this one, where we solve this problem in L. Okay, and so the next problem is, well, the idea to find an equilibrium, that we will look at a strategy which is equalizing P bar if the payoff in this game is in fact independent of the choice of history. All histories are best reply. This is okay for player 1. So we expect this to be a constant, and in fact there exists only one such equalizing strategy, and to find it easily just introduce, this is a mathematical trick, just introduce the probability lambda n, under which the UQ are IID with probability half 1 and probability half minus 1. Okay? So this is lambda n, denote S and Q the sum. Then this is a function of the whole history. Okay? And in fact, it can be expressed, it's quite easy to see, as the expectation of this under lambda n plus a sum of coefficients that depend on the path times UQ. Okay? And the explicit formula, this is why it's important, it's useful to introduce lambda n at this point, is that you can write easily those formula, those coefficients, gamma and q, okay, which are just this expectation under lambda n of this difference. Okay, but now from this equation, you replace this by this in that equation, and the result must be independent of UQ. It must be the case that P bar Q coincide with this gamma n Q. So gamma n is the unique equalizing strategy. And if you look now at this, clearly it's a martingale, because it's expectation under lambda n. Okay? And lambda n will be, in fact, the unique martingale equivalent measure. Okay? Now, I only have 5 minutes, so the idea then, you have the notion of equalizing strategy. The idea is to select a best reply, P, to this strategy, which is just pure best reply would be a choice of one history and an L in this set. So pure best reply will simply be a lottery on history and L, satisfying that with probability 1 you are in this. And we are now seeking for a pi such that gamma n is a best reply to this. Okay. Now, player 2's payoff will be this one, okay, under pi. Now, since you know that L is in the upper gradient, you know Fenchel relation, which is here. And so you can express this, well, we had an expression for this using lambda n, remember? Okay. And so the payoff of player 2 now, in terms of delta, which is its deviation from gamma n, is f of delta is the expectation of all these. Okay, so it depends on L and this. So now you want this, which is, by the way, due to the convexity of H, it's a convex problem in delta. You want to find an optimal solution, so you look at the first order condition. Okay, and what are those first order conditions? Well, you take the derivative with respect to epsilon of epsilon delta, you get an H prime here, multiplied by the coefficient of epsilon, which will be this one. Okay, and so now basically, since this depends only on you, you can take the conditional expectation also with respect to u. And now just observe that since H is increasing, this is a density. This is basically a density because it's positive up to a constant. And what this first order condition just tells you is that up to a constant, this is expectation under a new probability P tilde of this sum, okay, because this is incorporating the density. And so the only probability distribution such that this holds for all progressively measurable delta is the lambda n. And therefore, this p tilde is lambda n. And this is how we get the first announced result, that there exists, I mean, we know that there exists a probability distribution under which is lambda n, under which the process is of price must be a martingale. And in fact, we get that pi is an equilibrium if and only if pi gamma n. This has probability 1. The density is C minus 1y, with y being this expectation. Okay. And well, from this now you can start analyzing the asymptotic. And okay. And since I have no time, I will just skip and go to the last. You can apply this, okay, and you get, in fact, pretty nice result.
Were you talking about the square root of n because when you, which is of course for any one given finite approximation is completely irrelevant, but you always did it. Is that because there's a theorem that I missed that the distribution of final positions verges to a finite limit when you divide by the square root of n?
Yes. Yes, otherwise it go to infinity.
But that would suggest also that if you divide it by, for instance, if you divide it by n is the total number.
If the average,
if you do it, forcing an absolute volume of trade over the n periods that equal to n. We're forcing them. These people do not have a no trade.
Yes, yes.
They must trade. So if we divide it by something smaller, then in fact we have a price discovery algorithm that doesn't force the market maker to lose money. If you divide, for example, we divide it by n, then you actually have a virtue of the model because now you're no longer forcing them to lose money.
Okay, divided by n, but I only divide by square root of n.
Price discovery is the same.
Yes, 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 indeed. The price and the yes.
What we talked about was not the impoverishment of the market maker, but was about the price discovery process.
Yes, yes, yes.
So it was a bit jarring that we're forcing the market maker to lose money, but just a thought.
Okay.
Another question.
How many parameters do you?
Oh, well, I should explain. I mean, this is all a computation. So just to say that it cannot be applied to edge in a situation where Black and Scholes is not working, where there exists a smile of volatility, when we know that. So observing a bunch of coal today, which same expiry, I basically may predict what will be the dynamic up to the expiry, okay, by using that property that if I know the distribution, the final distribution of a CMMV, I know the, so I could basically, what this is, I observe at date 0. Those are calculations that are made at date 0, okay, observing a bunch of calls on CAC 40 at date 0. And what I was predicting is a blue line, okay, which is, but the blue line depends on the price. It's a relation between the price at date 20, between the calls and the underlying, okay?
So I guess
those are okay. Those are the strike of the call, and those are the market prices. Sorry.
Strike price and the market.
Observed market price, and what I am telling you is that if you give me the price of the underlying at date 20, you give it to me at date 0, I can compute this line. This is a pricing formula. It gives you the price of a call as a function of the underlying asset. Okay, so now.
What do you assume about the final distribution? That will be final, because you say call.
Just observing the call at date 0, I have no assumption. I mean, the only assumption is that the one.
What is mu? What is mu?
This is, in fact, what is nice here. You don't need to know. You compute it from the observation of the calls. Well, let me go there then. So the conjecture is that under the risk neutral probability, you have CMMVs. Okay? So let ST denote the forward, the actualized price of the underlying asset. CKT is the forward price of a European call with check K at maturity 1. Okay? As we know is that the price at date 0 is the expected under the martingale equivalent measure of the final price, which gives you this. So from date 0 observation, basically if you know this for a bunch of K, by derivation you get basically the law of S1. Okay, so you know the law mu of S1.
That's what makes it a martingale. That's what you mean.
You know the law of S1 just by the okay. Now, since you know the law at time 1, you can find the unique function which is increasing in x such that S1 will be f of B11 and with law 1. From this, you can compute the whole function f. Okay. And so you get ST is this function that you can compute numerically now of BTT. At time t, suppose that you observe that ST is this. Okay.
Date 0 observations are for all K.
Hmm?
The date 0 observations are
For all K, yes. For all K. Yes. Okay. So now, we assume that we observe ST, but since this function is increasing, it's monotonic in B, you can recover B. Okay. Now, what we know is that the price at time t will be this expectation given the past. So you know that S1 is this function f mu. This is this function. Well, this is typo. I should have put fb11. Okay, minus k plus given bt. But now you know the law, conditional law of b1 given bt. So basically, what you get is a relation. The price of the call is a function of the strike that depends also on time and on the current value at time t. And what was, so this is date 0 observation. Those are the dots on which I've based my computation. Okay, so it's not surprising that at date 0 my prevision is perfectly correct. What is more surprising is that with no additional value except that this is the only value I get, then you can say that the call should be on that line, and you see that it fits quite well. This is what, and this is, by the way, Black and Scholes. This is the red line. Okay. Black and Scholes is the red line, and the green line is the usually used way to compute in the market, which is the sticky strike. And I mean, the idea is that for all call at date 0, they would compute the implied volatility, and now they will suppose that this implied volatility will not move with time, and this is the one they will use to compute the price at date k. But, okay.
So we'll reconvene at 11:30. There is coffee and refreshments.
Very good.
Mm-hmm.
I had another question. I didn't want to hold out there.
because it was already running late. So you have the trading game, yes, which is an abstract thing per period, and then you look on the limit of n. But if you would like to think, okay, that you want to look on a period of 1 year, so the period is given, but you would like to change the duration of a trading time, a period. You have to modify, in some sense, the trading game, right? To make if there is a need, the assumption is that there is a need of an amount.
Oh, sorry.